97% efficiency sounds impressive, but what does it actually mean for you on the road? That number hides a year of failure and one team that refused to quit. Forget the specs for a moment. This is a story about engineering under pressure. Imagine a room full of engineers staring at battery cells scattered everywhere. They are not just building a battery pack right now. They are chasing something the industry has never quite achieved before. The goal was simple on paper, but brutal to execute in real life. Build one of the most energy-dense packs ever created for a vehicle. The lead engineer spent an entire year inside battery chemistry and cooling. Every single week brought a new problem to the table. Every month brought a fresh solution that changed everything again. That is engineering in its rawest form. Messy and relentless. The team never started from a completely blank sheet of paper. They studied production packs already out in the real world. They looked closely at what worked and what failed completely. They studied what could be improved with smarter thinking and better materials. That is smart engineering, not reinventing the wheel without reason. They borrowed the best ideas already proven across the industry. Then they layered their own proprietary technologies right on top. This combination created something genuinely different from anything else available. A pack built specifically for one very unusual and demanding vehicle. That vehicle needed a 42 kW battery for its launch edition. Every layer and every cell had to earn its place inside. Weight matters enormously when you chase maximum efficiency and range. Renderings show how everything fits together in careful layers. Each layer plays a specific role in protecting the battery safely. They keep it cool and performing at peak under real conditions. Look closely and you will notice cooling plates beneath the modules. These plates are not just decoration for marketing materials. They are the answer to one of the most debated questions online. Forums have been buzzing for months with pure speculation. People have been guessing and arguing without any real information. Is this battery air-cooled or liquid-cooled? They keep asking. Here is the answer straight from the people who built it. The battery is liquid-cooled for hot environments and demanding drives. It is also liquid-heated when temperatures drop too low outside. Whether the battery needs cooling or heating depends entirely on weather. Hot climates call for aggressive cooling to protect the cells. Cold climates call for heating to maintain optimal performance levels. Liquid handles both jobs better than air could ever manage alone. This thermal system keeps the battery in its ideal temperature range. That consistency protects performance and long-term battery health. While one team obsessed over chemistry, another focused on powertrain. Their mission was just as demanding as the battery challenge. Build something lighter and more efficient than anything else. Build something simpler with fewer parts and less complexity. The powertrain team worked closely with an outside partner. They co-developed a propulsion device unlike anything currently on the market. Fewer parts meant less weight and more efficiency from every watt. The result, they claim, is the most efficient powertrain available today. That is a bold statement, but the numbers tell a compelling story. Look at the power curve, and you start to understand the challenge. The standard motor from their partner was efficient in a different way, but it was efficient in the wrong regime entirely for this vehicle. That original motor was built for heavy vehicles carrying substantial loads. It performed best under high stress and high weight conditions. That is simply not the situation this lightweight vehicle lives in. This particular vehicle is remarkably light and slippery through air. It produces virtually no drag resistance while cruising at speed. That puts it in a completely different load regime than expected. Engineers realized quickly that a heavy load motor would waste energy, so they made a decision that changed everything about the project. Redesign the motor from the inside out piece by piece. They changed the windings inside the motor completely. They rearranged the magnets to shift the efficiency curve entirely. Every adjustment aimed at matching how this vehicle actually drives. This vehicle spends most of its life cruising at higher speeds, not grinding through heavy loads like a truck would do. So the motor needed to be efficient exactly in that zone. The redesign paid off in ways that surprised even the engineers. Efficiency improved tremendously once the motor was properly tuned. Tuned specifically for high-speed cruising, not low-speed hauling. That is the opposite of what most electric motors are built for. There is something else worth noticing in the motor design. Most people would overlook this detail completely, but engineers noticed. The upright connects the motor to the suspension system directly. That upright is actually part of the motor itself now. That single design choice eliminated extra parts and complexity. Fewer parts mean less weight and better overall vehicle efficiency. It also makes assembly dramatically simpler on the production line. Fewer components bolted together means fewer things can fail later. Fewer hours spent on the line and a cleaner build process. To be clear, this is not the original motor from their partner. This is a completely reimagined version developed specifically for them. It matches the unique demands of this unusual lightweight vehicle perfectly. Batteries and motors are only part of the larger equation. Getting power from one to the other efficiently requires something overlooked. The inverter is quiet, but absolutely critical to the whole system. The team developed a silicon carbide inverter alongside a nearby partner. Silicon carbide is not new technology, but this application is special. Using it this precisely changes everything about vehicle efficiency. Most inverters in the industry today run around 92% efficiency. That sounds impressive until you hear what this team achieved. Their new inverter runs at an astonishing 97% efficiency. That 5% gap might sound small on paper, but in real-world terms it changes the entire energy equation. Every bit of energy lost inside an inverter forces compensation. The battery must make up for every electron wasted in transit. Lose electrons and the battery simply has to work harder. A less efficient inverter forces the battery to push more power. More power means a bigger, heavier, and more expensive battery pack. By building a more efficient inverter, the team flipped that equation. Less energy lost means less power the battery needs to supply. Everyone benefits from this smarter approach to energy management. Money saved on battery size gets reinvested into better technology. They built a more advanced inverter capable of even greater efficiency. This new inverter carries a name inside the engineering team. They refer to it simply as the next revision internally. It is not just more efficient, it is significantly smaller physically. A smaller footprint matters more than most people realize. Less space for the inverter means more room for other systems, or simply a lighter and more compact overall vehicle design. The team is holding back a full rendering for now. Every good story needs a bit of mystery saved for later. What makes all of this possible comes down to one material. Silicon carbide is the core enabler behind every efficiency gain. Without it, none of these improvements would even exist. Traditional inverters rely on older semiconductor materials entirely. Those materials simply cannot match silicon carbide in any category. Switching speed and heat tolerance are dramatically better here. Overall energy efficiency under load is far superior as well. Choosing silicon carbide was not a small or easy decision. It required new manufacturing processes and entirely new partnerships. It required engineering expertise most teams simply do not have. But the payoff justified every bit of that difficulty. A smaller, lighter, more efficient inverter reduces battery capacity needs. Step back and look at the bigger picture forming here. Battery, motor, and inverter are not three separate stories. They are one connected system working together seamlessly. Every improvement in one area ripples outward into the others. A more efficient inverter directly reduces battery demand significantly. A better motor design reduces energy waste across the board. Everything compounds together layer by layer progressively. That is the real story behind this engineering update. Not a single breakthrough, but a series of connected decisions. Each one building on the last toward one shared goal. The goal was never just building a battery pack alone. It was never just building a motor or inverter individually. The goal was building an entire optimized system for one vehicle. One unusual lightweight vehicle that breaks all industry assumptions. Most vehicles on the road today are heavy and inefficient. They are built with components optimized for hauling heavy weight. They fight drag and survive harsh high-load driving conditions constantly. This vehicle breaks that mold entirely with its lightweight design. It is efficient by design from the very first sketch. And that meant nothing off the shelf would truly fit its needs. So the team built almost everything from scratch or heavily modified. That is a harder path that takes much longer. It costs more time, effort, and money to pursue. But it produces something genuinely unique and remarkable. A pack motor and inverter all tuned specifically for one vehicle. Tuned for actual driving behavior, not generic industry averages. Think about how rare that level of customization actually is. Most manufacturers use shared platforms across many different vehicles. They use shared motors and shared components everywhere. This team chose a harder, slower, more expensive path instead. They chose precision over convenience every single time. They chose performance tuned for this vehicle's real-world behavior. That decision shows up everywhere in the engineering details. The liquid cooling system and the redesigned motor windings. the integrated upright and the silicon carbide inverter. Every piece tells the same story of precision engineering, driven by a clear understanding of how this vehicle behaves, not theoretical specifications sitting on a page somewhere unused. Consider the cooling system for a moment longer carefully. Liquid cooling and heating together protect the battery completely. Extreme heat can degrade battery cells quickly if left unmanaged. Extreme cold can reduce range and performance dramatically. A liquid-based thermal system solves both problems simultaneously. That level of thermal control was not accidental at all. It came from analyzing failures in other production battery packs. Learning from others is not weakness, it is smart strategy. The team studied what worked and what failed completely. They built something smarter using lessons learned the hard way. Now consider the motor redesign again because it deserves attention. Changing windings and magnet arrangements is not a small tweak. It reshapes the entire efficiency curve of the motor. Most motors optimize for a narrow band of operating conditions. Push them outside that band and efficiency drops fast. This vehicle needed a motor built differently from the ground up, by shifting the efficiency curve toward high-speed cruising speed. The team matched the motor to how this vehicle actually drives. That is the difference between borrowing and truly co-developing. It requires deep collaboration and shared data between teams. It requires a willingness to rebuild things from scratch. The integrated upright design deserves attention as well. Combining a structural suspension component into the motor housing, that is not common in automotive engineering at all. It takes careful engineering and extensive testing to perfect. Get it wrong and you risk structural failure under stress. Get it right and you save weight and reduce parts. This team got it right through careful analysis and testing. Fewer parts, less weight, and easier assembly all together, all while maintaining structural integrity for real-world driving. Now think about the inverter story one more time, because efficiency gains there ripple outward into everything else. A 97% efficient inverter is not just marketing hype. It directly reduces how much battery capacity the vehicle needs. Less battery capacity needed means a lighter vehicle overall. A lighter vehicle needs less energy to move forward. Less energy needed means even better efficiency across the system. This is the compounding effect engineers dream about constantly. Small improvements in one area create bigger improvements everywhere. They snowball into a dramatically more efficient vehicle design. That snowball effect is exactly what happened with this project. Battery improvements enabled motor improvements progressively. Motor improvements enabled inverter improvements in return. Inverter improvements reduced battery demand right back again. It becomes a cycle of continuous refinement and improvement, each system pushing the others toward greater efficiency, lighter weight, and better performance across every driving condition. Engineering stories like this rarely get told in full detail. Most people only see the finished vehicle at the end, not the year of decisions shaping every single component. Behind every spec sheet number sits months of testing, months of redesigning, failing, and trying again relentlessly. The 42-kilowatt battery pack did not appear overnight. It evolved constantly through iteration and real testing. The 97% efficient inverter did not happen by accident. It came from deliberate material choices and careful partnerships. It came from a willingness to rebuild standard designs completely. Even the motor cope developed rather than borrowed directly. It represents months of collaboration between two engineering teams, working together to solve one very specific, unusual problem. That problem, simply stated, was build a propulsion system. Build it for a vehicle unlike almost anything else on the road. Light, efficient, and with incredibly low drag resistance. Solving that required questioning assumptions built into standard components. Standard motors, inverters, and cooling systems were not good enough. So the team rebuilt what needed rebuilding completely. They kept what worked and discarded what did not work. Slowly, piece by piece, an entirely new system took shape. This is what real engineering progress looks like inside. Not a single dramatic breakthrough, but steady accumulation. Smart decisions made consistently over many months of work. Liquid cooling instead of air cooling for reliability. Redesigned windings and magnets to match an unusual load regime. An integrated upright to reduce weight and simplify assembly. A silicon carbide inverter to push efficiency beyond industry standards. Each decision alone might seem small and incremental. Together they represent a fundamentally different engineering approach. An approach built from first principles, not assumptions. It prioritizes the actual behavior of the vehicle always. It asks a simple question repeatedly throughout the process. What does this specific vehicle actually need to perform? Not what a heavy sedan or SUV needs typically. What this lightweight, low-drag vehicle needs for maximum efficiency. That question shaped every engineering decision described here. The battery pack design and the cooling system choice. The motor redesign and the inverter development, all driven by that same relentless question about performance. It is a refreshing approach in today's automotive industry. An industry dominated by shared platforms and generic components. Components stretched across many vehicle types regardless of fit. This team chose specificity instead of generic convenience. They built exactly what their vehicle needed to succeed. Even when that meant more work and more testing. Even when it meant more time refining tiny details. The payoff shows up clearly in the final numbers. Inverter efficiency at 97% is remarkable achievement. Motor efficiency at cruising speeds improved dramatically too. A battery pack tuned specifically for its actual load. But numbers alone do not tell the whole story. Behind every percentage point sits a team solving problems. Problems most people never even think about seriously. Cooling plates hidden beneath modules drivers never see. Wendings inside a motor casing few will ever open. A silicon carbide inverter tucked away doing its job. Every single time the vehicle accelerates or cruises. Every time it slows down in any weather condition. These are the unseen details that determine real performance. They determine whether a vehicle actually delivers on promises, or simply looks good on a spec sheet without delivery. This engineering update pulls back the curtain on details. The liquid cooling debate is finally settled conclusively. The motor redesign is explained clearly and honestly. The inverter efficiency story is told in full detail. For anyone following online speculation and forum debates, for anyone guessing how this vehicle actually works. This update answers the biggest lingering questions directly. Is the battery air-cooled or liquid-cooled, they wondered. Liquid confirmed directly by the engineers who built it. Both cooling and heating depending on the environment. Is the motor a standard off-the-shelf component at all? No, it has been extensively redesigned for this vehicle. New windings and rearranged magnets tuned specifically. Is the inverter just another industry standard component? No, it uses silicon carbide technology for superior efficiency. Efficiency numbers well above typical industry averages today. These are not small claims being made lightly. They represent a genuinely different engineering philosophy, applied consistently across every major system in the vehicle. A philosophy built around one simple powerful idea. Match every component precisely to the vehicle's behavior. Do not force the vehicle to adapt around generic parts. That idea sounds simple when you state it plainly. Executing it across an entire system takes enormous effort. Battery, motor, and inverter all working in harmony. This story captures just a portion of the larger effort. The renderings shown represent months of careful design. Behind each image sits simulation testing and refinement. Hours of work that never make a presentation video. That is the nature of real engineering work. Slow, iterative, and often invisible progress over time, eventually producing something people can see and touch. The battery pack, motor, and inverter represent that progress. Invisible work made visible through honest transparency. There is more still to come from this team. A fuller look at the smaller, advanced inverter revision. The team is holding it back for a future reveal. For now, this update offers a clear look inside. It shows how everything was built around real needs. The needs of an unusual lightweight, low-drag vehicle. It is a story about questioning every single assumption. About rebuilding standard components with purpose and precision. About chasing efficiency through careful, deliberate choices. From liquid cooling plates hidden beneath battery modules, to redesigned motor wendings you will never see, to a silicon carbide inverter pushing past 97%. Every piece connects to form something greater. These systems form a powertrain built for one purpose. Executed with real precision born from months of collaboration, testing, and careful redesign of every single system. That difference is what shapes how this vehicle performs. Once it finally hits the open road for real.